is to claim that there is an unanswered question about the universe. And actually, he goes on to say that many religions committed iconoclasm, actually, by giving this quite abstract idea far too many properties that it never should have had. And of course, that's what we get served up as kids, this kind of rather silly version, and we reject it quite quickly. I certainly did when I came up to my comprehensive school, started learning a bit of science, and it just, the whole thing didn't make sense at all. But maybe we threw too much out with that, and maybe there is something interesting to see there. The unknown, and of course, they were those unknown volcanoes, earthquakes, and things. And what if science has got to know more and more about in fact, it's of course, the guest, which is Jackie was a derogatory term raised by This is Henri Poincaré, who discovered the mathematics of chaos theory at the beginning of the 20th century. And he explained how even if you do have the equations, and you have a very good description how the thing is set up, just a very small error can cause your predictions to be completely untenable, and something completely different can happen. And this can control just very simple systems, which use it to keep track of time. But this is a slightly different pendulum I've got here. It's called a double pendulum, so it's got two pieces of metal jointed together a little bit like a leg. So the geometry, mathematics of this is very simple to describe these two pieces of metal. The physics which controls how this will fall is also not that complicated, but being able to use that to predict the behaviour of this thing is almost impossible. Whoa! Oh, look at that. And I think the fact that you're laughing is a perfect example of the fact that this is unpredictable. Laughter is a response to, whoa, I wasn't expecting that to happen. But the real challenge of chaos theory that Poincare raised is, okay, that was very complex behaviour, but can I repeat the exact same behaviour? And actually, I have a little notch here, and I try to start the pendulum off in exactly the same place. So let's see whether, if you can remember what it did before, is it going to do... Whoa! That's already doing something completely different. I mean, it's still quite funky, but okay. And then it seems to. This is my favourite desktop toy. I can play with this for absolutely hours. So if you'll indulge me, I'm just going to do one more because it's just. Whoa! Oh. Whoa! I mean, where did that come from? Unbelievable! So this is the challenge of chaos theory. It actually gives very complex behaviour, but it's being able to repeat that behaviour. So I've got another desk, which I have on my desk at home. It's again a pendulum, but it's got 6 magnets which attract the pendulum, and over each magnet is actually an answer to a question. So I use this to make all my decisions in life, actually. So you can ask me a question. So for example, should I make a bet on Arsenal beating Swansea on Saturday? So we're going to sort of set this thing going. So the answer is like, try again. No way, definitely, maybe, yes, ask a friend. So here's a little one we did in the lab. So this is an example of this pendulum. I've got just 3 magnets here, but you try and predict which magnet the pendulum is going to end up at. You know, it wobbles between them all. Is it going to end up at the top one? And then right at last, it ends up at the bottom one. But it seems incredibly. So here we go. Maybe, right? I don't know. So actually, the challenge here, this is a bit like an asteroid flying around, and the magnets are like planets, and you've got to try and decide which planet is going to get wiped out by this asteroid. In fact, Poincare discovered this chaos theory when he was trying to understand the solar system to see whether the solar system was stable or not. And what he always says, definitely, great, yes, always right. And he understood that even the solar system, trying to predict whether that is stable or not, it's incredibly sensitive to just very small changes in where the asteroid is. So here's 3 computer models that I did of where the pendulum is going to end up. So I've coloured those 3 magnets, yellow, red, and blue. And I've started the pendulum off in the top left-hand corner. The first experiment, the thing wiped out the blue planet, but then I changed the 6th decimal place of one of the coordinates of the starting position. So you can't even see that it's changed, but when I then ran the model, well, it sort of followed the same path for a while and then completely veered off and did something completely different. That time it wiped out the red planet. Then I changed the 6th decimal place again. Again, it's similar sort of trajectory to start with, and then wipes out the yellow planet. So that very small change causes a massive difference in the outcome. So this is incredibly difficult to predict, even though I have the equations and I might have very accurate knowledge about the starting position. Unless I have complete knowledge, I really cannot know what the answer is going to be. And this computer graphic helps you to try and make a prediction about where the pendulum will end up. So if I start the pendulum over a yellow region, that means that the pendulum is going to end up at the yellow magnet. So you can see there are some regions which are knowable. I mean, so the yellow magnet is sitting under that big yellow blob there, and sure enough, I start the pendulum next to the yellow magnet, then the other 2 can't pull it, and so it's just going to wobble and then settle on the yellow magnet. There's another area sort of opposite the yellow magnet, which if I start it there, it's again quite predictable. A little error won't cause it to do anything terribly different. It will just swing backwards and forwards, and eventually the other 2 magnets can't each of these edges, an expert in this area, somebody who's been at this edge trying to push it ever further. So the expert I took actually on my journey to try and predict the future was a colleague of mine in Oxford, Bob May, who's a mathematical biologist, and he was one of the people who understood that population dynamics, very simple sort of feedback equation which controls the population of animals from one season to another, can also have this incredible sensitivity to small changes.